You learned that nothing can go faster than light. That's not wrong. And yet right now, tonight, there are galaxies moving away from us faster than light travels. Both of those things are true at the same time. Sit with that for a second, because I'm not going to rush past it. Either Einstein got something wrong, or all of us have been misunderstanding what moving even means. I'll tell you right now, it's the second one. And once you see why, you're going to look at empty space completely differently. Here's the assumption we have to break first, because everything else depends on it. You picture space like an empty room, a stage, and galaxies are like balls rolling around on the floor of that room. Some roll fast, some roll slow. But the room itself, the room just sits there doing nothing, holding still while the balls move through it. That picture is the whole problem. That's the thing we have to throw out. Space isn't a stage. Space is part of the show. Think of a rubber sheet with dots drawn on it, not moving, just sitting there, marked in place. Now stretch the sheet. Pull it outward from every direction at once. What happens to the dots? They separate. They get farther apart. But did any single dot move across the surface of the rubber? No, not 1 inch. The dot didn't go anywhere relative to the rubber it's sitting on. The rubber itself just got bigger and carried the dot along with it. That's what's happening with galaxies. The speed limit, the speed of light, that rule applies to things moving through space. A rocket, a photon, information, anything traveling from point A to point B across the fabric. It says absolutely nothing about the fabric itself stretching. A galaxy can be sitting still, doing nothing, minding its own business, obeying every law of physics perfectly, and still get carried away from us faster and faster, just because the space between us and it is expanding. It's not breaking the speed limit. It's not even on the road. Now let's make this precise, because space is stretching is a nice phrase, but I want you to actually feel the mechanism, not just nod along with a metaphor. Here's Hubble's law, and it's beautifully simple once you see it. The farther away a galaxy is, the faster it appears to be receding from us. Not a little faster, proportionally faster. Twice the distance, twice the speed. Go back to that rubber sheet. Mark dots in a row, evenly spaced, say 1 inch apart. Now stretch the sheet so every inch becomes 2 inches. The dot that was 1 inch away is now 2 inches away. It moved 1 inch. But the dot that was 10 inches away, now it's 20 inches away. It moved 10 inches in the exact same stretch, the exact same amount of time. Same expansion, same rule book, but the more distant dot appears to have moved much faster, purely because there was more space between it and you to begin with, and all of that space stretched simultaneously. Nothing is favoring the far dot. Nothing is giving it extra speed. There's just more stretching fabric piled up in the gap. Now do the arithmetic for real. Push that distance out far enough, past roughly 14 billion light years, and the cumulative stretching across all that space adds up to more than the speed of light. Not because any single patch of space out there is doing anything unusual. Every patch is stretching at the same modest rate as the patch right here around you, right now. This room, this air, expanding almost imperceptibly. But when you add up that tiny rate across billions and billions of light years worth of space stacked end to end, the total crosses the line. That boundary has a name, the Hubble radius, sometimes called the cosmic horizon. Past it, galaxies are, in this technical sense, receding faster than light. And I want to flag something here, because it matters and people skip past it. Naming that boundary is not the same as explaining it. Calling it the Hubble radius just tells you where, on the map, the naive version of the speed limit stops applying. It doesn't tell you why space stretches, or what's doing the stretching, or what stretching space is actually made of underneath. We'll come back to that. Hold on to it. Because here's where it gets genuinely strange, stranger than the setup even. If a galaxy is receding faster than light, how do we ever see it? Shouldn't its light just be stuck? Like a swimmer trying to swim upstream against a current stronger than they can push. That's actually the right picture. Hold it in your head exactly like that. A photon leaves a distant galaxy and it starts swimming toward us, through space that is stretching, expanding, working against it the entire way. Early on, at the galaxies beyond that horizon, the current is stronger than the swimmer. The photon actually loses ground, net, even while swimming as hard as physics allows, which is to say, at the speed of light through its local patch of space. So how does any of that light ever reach us? Because the current itself isn't constant. The expansion rate of the universe has changed over its 13.8 billion year history. It was faster in some eras, slower in others. So a photon can start out swimming against a current that's too strong, get swept backward for a while, and then as the expansion rate eases, the current weakens beneath it, and eventually the swimmer's own effort starts to win. It breaks through. It crosses whatever ground it needs to, and eventually, billions of years later, it lands in our telescope. That is a real working explanation. It's not hand-waving. It comes out of general relativity applied to an expanding metric, and it fits an enormous pile of observational data: supernova brightness, the cosmic microwave background, the large-scale structure of galaxies. It's one of the best-tested frameworks we've got. But, and I want to be completely honest with you here, because pretending otherwise would be a kind of lie, the specific details of that expansion history are not fully settled. There's a number called the Hubble constant. It tells you how fast the universe is expanding right now, today. We measure it multiple independent ways. One method looks at nearby stars and supernovae. Another looks all the way back at the ancient light of the cosmic microwave background. And those two methods give us different answers. Not wildly different, but different enough and consistently enough that it's not just measurement error anymore. Scientists call this the Hubble tension, and nobody has nailed down whether it means our instruments are slightly off or whether it means something about the underlying model of the universe's expansion is incomplete. So when I tell you the light broke through because the expansion rate eased over time, that's true, and it's the accepted framework, and it fits beautifully in aggregate. But ask a sharper question. Exactly how fast was space stretching at every single point in cosmic history, down to precise numbers we can all agree on? And the honest answer is, we're still working on it. We don't have that pinned down perfectly, not yet. And there's a deeper layer under even that, one I don't think anyone can currently answer at all. What is space, actually, that it can stretch like this? Not move through itself, stretch. What is the thing that's expanding? We can describe the stretching mathematically, with exquisite precision. General relativity hands you the equations, and the equations work. But asking what's physically doing the stretching, what space is made of such that expansion is even a coherent thing to happen to it, that question doesn't have a mechanical answer. It might not even be the kind of question physics, as we currently understand it, is built to answer. We're not being coy when we say that. We genuinely don't know, and I'd rather tell you that plainly than dress it up as something more settled than it is. Now here's what actually keeps me thinking about this one. Long after the physics part is done, most of the universe, most of it, by a wide margin, is already permanently out of our reach. Not far away in the ordinary sense, where if we just waited long enough or traveled fast enough, we'd eventually get there. Unreachable, forever. There are galaxies out past that horizon right now whose light will never cross the gap to us, because the gap between us and them is growing faster than light can close it. Not slower than light, faster, permanently. The math doesn't allow it, ever, no matter how much time passes. And this isn't a special property of Earth or of us. Every observer, everywhere in the universe, sits at the center of their own personal horizon. Some alien astronomer 4 billion light years away has their own bubble of the reachable, and it's shrinking too, for exactly the same reason ours is. Nobody is special here. Nobody's in a privileged spot. That's just what it means to live inside something that's expanding. You get your own little bubble of what's knowable, and the bubble gets smaller every year. And there's nothing anyone can do about it. Somewhere out there, right now, a galaxy is crossing that horizon, slipping past the point where its last photon will ever reach us. And we will never see it happen. We'll never get a notification, never see some dramatic vanishing. Its last bit of light is already on its way here, taking its sweet time, arriving in some far future, and after that light arrives, there is nothing more. That galaxy goes dark to us forever. Not because it stopped existing, but because the space between us and it simply grew too fast for anything to ever cross it again. We didn't break any laws of physics to find this out. We didn't discover some hidden loophole or some flaw in Einstein's thinking. We just looked carefully enough at the space between things, the emptiness we always assumed was just a passive backdrop, and found out the space itself was never empty, never still, never just a stage for the real action to happen on. It was the story the whole time. It was doing something, all along, quietly, while we were busy looking at the galaxies sitting on top of it. And most of that story, most of what's actually happening out there right now, this second, is one we will never get to read the ending of. I don't know about you, but I find that unbearably beautiful. Not because it's comforting, it isn't really, but because it means the universe is bigger than our reach, bigger than our instruments, bigger than the light that will ever touch us. And knowing exactly why, precisely, mathematically why, doesn't shrink that feeling one bit. If anything, it makes it sharper. We understand the mechanism, and the mystery gets bigger, not smaller. That's the strangest, most honest thing science ever hands you.